In this video, we're going to talk about how to express negative numbers in binary using the sign magnitude method and the 2's complement method. And later in this video, we're going to talk about how to add and subtract binary numbers using the 2's complements. So let's say if we want to write -6 as a number, how will we do that? So we're going to start with the sign magnitude method. In order to express -6, first we need to find out what 6 is. And we're going to use a 4-bit binary to do so. So 2 to the n minus 1, that's going to be 2 to the 4 minus 1, which is 2 to the 3, and that's 8. So this is going to be 8, 4, 2, and 1. So first let's express 6 as a binary number. 6 is 4 plus 2. So we're going to put a 1 in the column under 4 and 2, and we're going to put a 0 everywhere else. So that would be +6. In sign magnitude, the first 3 numbers corresponds to the magnitude of the number 6. The last number, 0, this corresponds to the sign. So if the last number is 0, that means we're dealing with a positive number. If it's 1, that means we're dealing with a negative number. So to express -6, we just need to replace this with a 1. So using the sign magnitude method, -6 is going to be 1, 1, 1, 0. And that will be the answer. Now let's work on some other examples. Using the sign magnitude method, let's express the following negative numbers in binary. And we're going to use a 5-bit binary system. So 2 to the n minus 1, that's going to be 2 to the 5 minus 1, which is 2 to the 4, and that's 16. So this is going to be 16, 8, 4, 2, and 1. So let's start with +7. Because this is positive, the first one is going to be 0. 7 is 4 plus 2 plus 1. So we're going to put a 1 under those numbers. So that number corresponds to 7. To get -7, all we need to do is replace this 0 with a 1. Remember, that first number indicates the sign. Everything else is going to be the same. So using the sign magnitude method, -7 would correspond to this 5-bit binary number. Now let's try -12. So first, let's find the number for 12. So the first number is going to be a 0, and 12 is simply 8 plus 4. So we're going to put a 1 under those two numbers. So that's the binary equivalent of 12. So now, let's find a -12. So we're just going to replace this with a 1. So it's going to be 1, 0, 0. 1, 1, 1, 0, 0. We're just changing that number into a 1. And so that's how we could represent -12 using sign magnitude. For the last one, -15, let's start with +15. So the first number is going to be 0. 15 is the sum of all 4 of these numbers. 8 plus 4 plus 2 plus 1 is 15. So we're going to put a 1 for all 4 of them. So to express -15, change the sign to negative. So this would be the 5-bit binary number that will correspond to -15. So this method of representing negative numbers, that is the sign magnitude method, is very easy for people to understand. It's very user-friendly. However, it doesn't work very well for computers, especially when computers need to perform operations, such as addition or subtraction. For instance, let's say if we want to add 7 and -7, we should get 0. So let's add these two binary numbers, 0, 0, 1, 1, 1, and 1, 1, 1, 0, 1. So 1 plus 1, that would be 2, but we can't really write 2, so we'll just put 0, carry over the 1. So this right here would be 0 carry over the 1, but we have another 1 plus this 0, which will turn this into a 1. So this right here would put a 0 and a 1 carryover, but the 0 part plus this 1 will give us another 1. And then we have 1 plus 0, which is 1, and 0 plus 1, which is 1. And this is 1, 2, 4, 8, 16. So we're adding 16, 8, 4, and 2. So the result that we'll get is not 0, as you can see. This would be 30, and that can't be right. So as you could see, when expressing negative numbers using the sign and magnitude method, it's not very helpful if we need to perform operations such as addition or subtraction. So now let's talk about expressing negative numbers using the 2's complement method. And we're going to see why this works out so well. So let's start with 7. So 7 is 0, 1, 1, 1. Now, what we need to do is find the 1's complement first. So we're just going to, every 1 that we see, we're going to replace it with a 0. And every 0 that we see, we're going to replace it with 1. Now, our next step is to add 1. That will give us the 2's complements. 0 plus 1 is 1. And then we could just bring down everything else. So negative 7 would correspond to the number that we see here. Now keep in mind, the first 1 that you see indicates a negative value. Now how can we quickly check to see if this is indeed negative 7? Because the binary equivalent looks like 8 plus 1, which is 9. But here's how you can check to see if it's negative 7. Remember, this 1 is associated with a negative sign. So if you make this negative 8, this becomes negative 8 plus 0 plus 0 plus 1, which gives us negative 7. So that works. So that's how we can represent a negative number. Let's try another example. So go ahead and represent negative 12 as a binary number using the 2's complements. So first we need to write 12. So this is going to be, we're going to use a 5-bit system. So 16, 8, 4, 2, 1. So the 0 would indicate that this is going to be a positive number, just like before. So that's why we're using a 5-bit binary system instead of a 4-bit, because we need the 8 to make 12. 8 plus 4 is 12. So 12 would be 0, 1, 1, 0, 0. Now, let's find the complement of this number. So replace 0 with 1 and replace 1 with 0. Next, add 1. So 1 plus 1 is going to be 0, carry over the 1. 1 plus 1 is 0, carry over the 1. Let me just separate these numbers from what we have below. 1 plus 0 is 1, and then we could just bring down the other numbers. So negative 12 is 1, 0, 1, 0, 0. So keep in mind, the first number is to tell us that it's a negative number. So now let's check our work. So we have a 16 here and a negative value. So that's going to be negative 16. We have a 0 in the 8 column, so we're not going to add anything. We have a 1 in the 4 column, so we're going to add a 4. And here we have nothing, so it becomes negative 16 plus 4, and that checks out. That is negative 12. So that is negative 12 as a binary number using the 2's complement method. So now let's talk about how we could subtract two binary numbers. We're going to go over two methods. The first one involves straightforward subtraction, and the second one involves the 2's complement. So let's do straightforward subtraction. 1 minus 1 is 0. 1 minus 0 is 1. Now, 0 minus 1, if we do that, that's going to be negative 1. And putting a negative 1 here just doesn't look right. So let's not do that. What we need to do is borrow something from this 1. If we borrow a 1, this becomes 0, and we get 2 1s here. Now, we're going to have a lot of 1s here, so that just doesn't look right. I mean, you could do it this way, it works, but the decimal equivalent of 2 1s is 2. So I like to represent this as 2. That's just my unconventional method of subtracting binary numbers. Now, we need to borrow a 1 from this 2. And so this is going to become a 2. 2 minus 1 is 1. 1 minus 1 is 0. And then 0 minus 0 is just 0. So now let's see if this actually works. So this is 1, 2, 4, 8, 16, 32, 64. So now let's convert these numbers into decimal numbers. So originally we had a 1 here. The decimal value for that is 32. Plus 4, that's 36. Plus 2, 38. Plus 1, 39. So the original number at the top was 39. And then we have a minus sign. This is 16 plus 8, that's 24. Plus 1, that's 25. So 39 minus 25, that's 14. Now let's see if this number actually represents 14. So this is 8, 4, that's 12, plus 2, that is 14. So this technique works. It's a very simple way of subtracting two numbers. Now let's use the 2's complement method. In this example, we subtracted two positive numbers. We had positive 39 minus positive 25. Now when using the 2 complements method, if you need to do subtraction, what you want to do is basically add a negative number. So this is still going to be positive 39. Well, I'm just going to write 39 to represent that. And then it's going to be plus negative 25. We're still going to get 14. But instead of having a positive 25 value here, we're going to have a negative 25. So I'm going to rewrite the 39 value as a binary number. So that's what we have in this row. Now, I'm going to change this part, which is positive 25, into negative 25. Using the 2's complement method. So first, let's rewrite it. Now, let's find the 1's complement of that number. So replace 1 with 0, and then replace 0 with 1. Our next step is to add 1. So this is 1, 1, 1, 0, 0, 1, 1. So this number should represent negative 25. And let's just check it to make sure that it does. So keep in mind, the first 1 represents a negative value. So that's going to be negative 64. So we have negative 64 plus 32. This corresponds to a 4. So that's plus 4, plus 2, plus 1. Negative 64 plus 32 plus 4 plus 2 plus 1. So that is indeed negative 25. So now I'm going to take this binary number and put it beneath this one. So that's 1, 1, 0, 0, 1, 1, 1. And now we're not going to subtract, but we're going to add. So remember, the top number is positive 39. The bottom number is negative 25. And we're adding, which is a nice way to do subtraction. So 1 plus 1, that's going to be 0, carry over the 1. Now this part here, 1 plus 1, that is 0, carry over the 1. But when you add this 1 and this 0, that becomes a 1. Now we're going to do the same thing here. 1 plus 1 is 0, carry over the 1, and then 1 plus this 0 is 1. Now we have 1 plus 0, which is 1. 0 plus 0 is 0. 1 plus 1 is 0, carry over the 1. 1 plus 1 is 0, carry over the 1. Now this is a carryover because we didn't have that many digits to begin with. So now let's see what answer we get. So with this extra carryover, you can just get rid of it because that's an overflow. That's going to be out of the range. So our real answer is what we see here, ignoring the overflow value. And you can see this is 8 plus 4 plus 2. 8 plus 4 plus 2 adds up to 14. So that's how we can do binary subtraction using the 2's complement. So what you want to do is, instead of subtracting a positive number, you make that a negative number and then just add it. But you have to get both of these numbers in binary form. So you can keep this number the same, but you got to find the 2's complement of this number, which takes a lot of work. So you have to choose, which method is easier for you to do. But that's how you would do it using the 2's complement method. Let's try another example of subtracting two binary numbers. So this is going to be 0, 1, 0, 0, 0, 1, 1, 1. Feel free to try this example. Now, before I subtract it, I want to get the decimal equivalent of each number. So this is 1, 2, 4, 8, 16, 32, 64, 128. So this is 32 plus 8, that's 40, 42, 43. And then we're going to subtract that by, this is 64 plus 4, that's 68, plus 2, that's 70, 71. Notice that the second number is larger than the first. Now this is positive 71. As we can see, the last number is 0. And this is positive 43. So when we subtract these two numbers, we're going to get a negative result. 43 minus 71, that's going to be negative 28. So will both methods give us a negative result? Or should we use the 2's complement method, or should we use the straightforward method? What would you say? It turns out that both methods will work. Let's start with the straightforward method. So we have 1 minus 1, which is 0. This is 0 as well. Here we have 0 minus 1. 0 minus 1 is negative 1. But you don't want to put a negative number when dealing with binary. So we need to borrow a 1. This is going to become 2. 2 minus 1 is 1. This is 0. 1 minus 0 is 1. Now, 0 minus 1, we have that situation again. But notice that we can't borrow a 0 here. And also, it's the last one. So, in this case, I'm going to put negative 1 here. Or rather, I'm just going to put 1 in parentheses to indicate that this is a negative value. Now, let's check the work. So we have 64, but this corresponds to a negative value. So that's going to be negative 64. And keep in mind, if the first number is a 1, it indicates a negative value. If it's a 0, it indicates a positive value. Next, we have 32. This one corresponds to 4. And then let's add what we have here. So negative 64 plus 32 plus 4. So this adds up to negative 28. So as we could see, it does work. So I'm just going to write the answer on the bottom. So this is negative 28 as a binary number. Just keep in mind, the first number 1 corresponds to a negative value. Now let's see if we can get the same answer using the 2's complement method. So we're going to, instead of subtracting, we're going to add. But this is going to be negative 71 as opposed to positive 71. And this should give us the same result, negative 28. So the first number, 43, we're going to keep the same, but we need to find the negative equivalent of this number. So let's get rid of this. Let's rewrite the top number, 0, 0, 1, 0, 1, 0, 1, 1. Just had to make sure I copied that correctly. So now let's change this value. And I'm running out of space. So I'm going to rewrite it here. Let's find the complements of all the numbers. So let's replace 1 with 0 and 0 with 1. And then we're going to add 1. So this is going to be 1, 0, 0, 1, 1, 1, 0, 1. So this should be negative 71. And let's just do a quick check to make sure that's the case. So this is 1, 2, 4, 8, 16, 32, 64, 128. Now the first number is negative, so that corresponds to negative 128. And then we have a 32, a 16. This one corresponds to 8. And the last one corresponds to 1. So negative 128 plus 32 plus 16 plus 8 plus 1, that adds up to negative 71. So that's the right number. We're going to put that here. So 1, 0, 1, 1, 1, 0, 0, 1. And now let's add these two numbers using this process. So 1 plus 1, that's going to be 0, carry over the 1. And then we have 1 plus 1 again, which is 0, carry over the 1. 1 plus 0 is 1. And then 1 plus 1 is 0, carry over the 1. Then we have 1 plus 1 again, which is another 0, carry over the 1. Now we have 3 1s. So the first 2 1s will give us a 0 and a 1. And then the remaining 1 plus a 0 will give us a 1. So let's turn that into a 1. And then we have 1 plus 0, which is 1, and then 0 plus 1, which is 1. Now, our answer looks similar, but not exactly the same. So this part here is exactly what we see here, 1, 1, 0, 0, 1, 0, 0. But we got this extra 1. So why is it different? Well, keep in mind that this is going to be our negative value. It turns out that even though we have an extra digit, so to speak, or an extra bit, the value is still the same. So this is 1, 2, 4, 8, 16, 32, 64, 128. So this corresponds to negative 128. And then we have a 1 in the 64 column. That's going to be positive 64. And then this is positive 32. And then we have positive 4. So let's do the math. Negative 128 plus 64 plus 32 plus 4 still gives us the same answer of negative 28. And this will also give us negative 28 as well. This will be negative 64 plus 32 plus 4, which is the same result. So the decimal equivalent of these binary numbers are the same. So we still get the same right answer. It looks a little different with the extra 1. So that's the end of this video. Now you know how to express a negative number as a binary number using the sign magnitude method and the 2's complement method. And you know how to perform binary addition as well as binary subtraction using the 2's complement method and the straightforward subtraction method. So thanks again for watching, and don't forget to subscribe.